Good morning, dear students. Welcome all of you to my nuclear chemistry class. Okay. Today I am going to discuss about some of the important aspects in connection with the nuclear chemistry or nuclear chemistry topics. First of all, I wish to discuss about the nuclear structure and stability. Okay. I want to draw your attention to the nuclear structure and the nuclear size, dimension, volume, density, etc. And then we have to account for the nuclear stability. Okay, why the need of accounting the nuclear stability? So we have to go for the theory for accounting nuclear stability. Okay, that is I wish to discuss in the following manner. That is the structure of the nucleus, size of the nucleus, that is radius and volume, and mass and density of the nucleus. Then going to say about the stability of the nucleus. Then we have to go for various theories accounting the stability of the nucleus, mainly N by P ratio theory, vacuum fraction theory, both are empirical theory. Okay, not much fully valid. And the more scientific theory comes the binding energy theory, or binding energy, stability terms of binding energy. And the important is nuclear attractive force theory, suggested by Yukawa meson-fold theory. Okay, meson-fold concept, the Yukawa theory. That is the most adequate explanation for the stability of the nucleus. Then based on that, we have to finally account a nuclear model of the nucleus. A good model for the nucleus, that is a liquid drop model or fluid model of the nucleus. That is your syllabus is framed like that. Okay, in this year, the degree level, you have to go through one of the model of the nucleus, that is the liquid drop model, other is called a fluid model, but there are various other models, Fermi gas model, there is the shell model and collective model. All these has to be, you will study in your higher classes. Okay, PG level you will study. Okay, first of all, I am going to discuss about the nucleus structure. All of you know what is a nucleus. That I think that in your plus 2 level you have studied that the scientist called Rutherford discovered the nucleus by the famous scattering of alpha particle with a thin gold foil. The gold, that is the scattering of the gold leaf experiment. So the scattering of alpha particle by thin gold foil experiment, I think that you are familiar, and thus experiment led to the discovery of the central positive part of an atom, that is called a nucleus. Okay, I am not going to discuss the Rutherford experiment. It is not the part of you. What is a nucleus? Just for memorization, just for recap, what is a nucleus? Nucleus is considered as the positively charged central core of the atom, in which the entire mass of the atom is concentrated or accumulated. That's the definition. Okay. Again, repeat. Nucleus is the central positive core of an atom, in which the entire mass of the atom is concentrated or accumulated. It's a very simple definition. Okay, you can say that central part of an atom which is positively charged and heavily massive. Okay, or the entire mass of the atom is called the heavy positive part of central part of the atom. Simple. The heavy positive central part of the atom is simply called nucleus. That's the definition. Okay. Then, what is the structure of the so-called nucleus? At the time of the Rutherford, just consider the structure of the nucleus as a symbol, because it is believed that a nucleus consists of only two massive species inside the nucleus, that is considered as the constituent of the nucleus. They are proton and neutron. The Goldstein discovered proton and James Chadwick discovered neutron in 1922-28. Okay. These two constituent massive particles together called nucleons. Okay, they are together called collectively called nucleon. So at the time of the Rutherford, it is believed that the structure of the nucleus is a simple, okay, consider simple. That means it consists of two massive species called proton and neutron collectively binding together inside the nucleus. Okay, therefore they are called constituent of the nucleus and they are called nucleons. But the present position is totally changed. It is different. The present position of the nucleus structure is changed considerably. It is different from the Rutherford time. The nucleus is now known to consist of more than or contain more than 100 subatomic particles along with our proton and neutron in associated with it. So you have to remember, at present it is found that a nucleus now contains large number of subatomic particles at least greater than 10,000 numbers. Okay, particles are associated and they are associated with different energy, different charges, different masses and different spin and different lifetime. So much complicated. So at present it has found that the situation of the nucleus structure is so complicated because of the discovery of more than 100 subatomic particles inside the nucleus which differ in their charge, which differ in their lifetime, which differ in their mass, which differ in their energy and which differ in their spin. And they often undergo interaction with each other. And the secret of the interaction is still uncertain. But how they interact. And next thing is that how all these particles are retained within the small nucleus. I am going to say stressfully, the volume of the nucleus is extremely small. Within the small volume, that is the order of 10 raised to minus 45 meter cube. Volume of the nucleus is only the order of 10 raised to minus 45 meter cube only. It's a very small value. Within this small nucleus, okay, these small volumes of space, more than 100 subatomic particles, charged, massive, stable or unstable, time undergoing change, interaction, etc. are retained. And how they exist there and how they are stable. You know that nucleus is extremely stable. The nucleus of most of the atoms are extremely stable except that of the heavy nucleus. You know, all you know that radioactive nucleus. Only the nucleus of the spontaneously disintegrating radioactive nucleus are unstable. That comes only after the mass number 200. Beyond mass number 200, the nucleus become unstable. They undergo spontaneous disintegration into radioactive nucleus. And after uranium, there is no stable nucleus found on the earth. They are called transuranic element, or all the transuranic elements are artificially synthesized. They are synthesized inside the lab, and the transuranium elements are all artificially synthesized. And now synthesis is going on, and now I think it will become 170. So the number of new elements now increase even up to 117 mass number. Sorry, that is atomic number. Atomic number 117. Mass atomic number now become 117 atomic number. Okay. So mass is much greater. I think mass 250, 270 like that it comes. Anyway, what I want to say, an atom is characterized by the atomic number. Okay. When we are studying in our PG class, I think that the periodic table contains only element up to 105, I think. All other elements, 113, 115, 110, etc. are speculated. Eka, mercury, Eka, something like that. Now, the number of elements now discovered now going to be atomic number 170, and name also is given. That aspect is given. I don't go into discuss that aspect because I want reference for the naming, etc. Because the new aspects I'm not just familiar with that. Okay. Anyway, the number of elements are going on increasing. There are newer and newer elements are added. What I want to say is that till now, the nucleus structure, the exact nucleus structure is still on contradiction or still not completely that is explained. So it is a subject of hot research, the hottest research. It is a subject of hot research in the theoretical physics. You know that most of the theoretical physics are involved in the research in the nucleus structure and also in the, that space. Okay, that is stellar region. That is the cosmic. All this. That means. I think that I guess space. In the space research. Okay, that the theory, Big Bang theory, all this. The space research and also nucleus research are the two important research fields, that is what research field in which the theoretical physics are still going on in numerous in number, and new inventions are going to be added one by one. So what I want to say is that the structure of the nucleus is still uncertain, the exact structure. There is no theory, not established to explain the stability or the interaction between various subatomic particles that is taking place within the nucleus. So what I want to give, I wish to give some innovation. Okay, intuition is that a high scope is there to carry out research in the theoretical branch of the theoretical physics or theoretical chemistry in the branch called the nucleus structure. And other is, I think, space science, then fusion, etc. Fusion is also a branch. Okay, I am not going to discuss all these aspects here. First of all, what I want to know is the structure of the nucleus that I have mentioned. So, the structure of the nucleus is still complicated. It contains more than 100 subatomic particles and more particles are now added here. Generally, okay, a nucleus is composed of two subatomic particles, mainly massive particles called proton and neutron. They are the chief constituent of the nucleus. They cannot be called fundamental particles. They are called constituent of the nucleus. They are the two massive particles generally, and therefore they are in all the time they are considered as the nucleons, together called nucleons. Generally, but this particle again are made up of other particles called quark. Okay, quark. The quark theory is there. That's quark and antiquarks. The neutron and proton again are made up of other particles, subparticles called quark and antiquarks. So generally, what I want to wish to say that the various nuclear particles can be divided into. Okay, now I mentioned that the structure of the nucleus is so complicated that more than 100 subatomic particles are discovered till now, and more particles are going to be added to the list. And they are all different, their size, mass, then spin, energy, etc. And they usually undergo interaction with each other, and the mechanism of the interaction reaction is still uncertain. Okay? The various nuclear particles can be mainly divided into two categories. What I want to sum up is that the various nuclear particles can be divided into two categories. Nuclear particles can be divided into two. Okay, into two. One is leptons, and other is hydron. One is hadron. Two is hadron. So the nuclear particles are generally classified into two. One is lepton. One class is lepton and other class is hadron. Okay. The lepton, which are infinitesimally small particles. Leptons are infinitesimally small particles and are by definition they are the fundamental particles. So leptons are infinitesimally. Okay. Leptons are infinitely, infinitely small particle. They are very small particle. Like electron, positron, neutrino and antineutrino. And they do not undergo interaction with any other particle generally, okay, and hence they are called fundamental particles. Generally, by definition, they are fundamental particles. Okay, that is the situation. But hadrons are which are bigger particles, or the size or the order of 1 femtometer, bigger particle, okay, which undergo interaction with each other, and they cannot be called fundamental particles. Okay, hadrons are bigger particles. They are very small particles like proton, electron, positron, neutron, antineutrino, etc. and they are considered as fundamental particles. But hadrons are bigger particles of the size of the order of 1 fermion, order of fermion, that is 10 raised to minus 15 meter, and they undergo interaction with each other. They cannot be called a fundamental particle because they can undergo interaction with each other. They cannot be called fundamental particles. Example are proton, neutron, meson, etc. Okay, proton, neutron, meson, etc. And again, this hadron itself, okay, hadron are in fact composed of smaller particle called quark or antiquark. These are in fact composed of smaller particles called quark, Q-U-A-R-K, quark or antiquark. For example, I want to mention proton and neutron are made of 3 quarks, while meson are made up of 1 quark and 1 antiquark. Okay, the quark are material that is built in itself, that is formed by itself. Okay, that never be discovered or never be physically identified. Quark are that is material that is made from that material inside. Okay, that is the thing. That is this composed small particle called a quark or antiquark. Okay, this is the situation. So what I want to mention is that the total subatomic particle and nucleus are now divided into 2 classes. One is lepton and the other is hadron. The leptons are infinitely small particles like electron, positron and neutrino and antineutrino. They are considered as fundamental particles. Okay, while hadron are considered as bigger particle, bigger in size, particle of bigger size of the order of fermion or femtometer, 10 raised to minus 50 meter, and they cannot be called fundamental particles. They can interact with each other. Proton, they are example of proton, neutron, meson, etc. And they can itself, they are made up of smaller particles. They are itself made up of smaller particles, composed of smaller particles, quark or antiquark. Okay, this is the main idea of the nuclear structure. That's all. What I wish to say is that there is no complete theory that will explain the nuclear structure, and the research is still holds, and the newer and new particles are added along the list of the subatomic particles, and various mechanisms or the theories are developed for the various types of interaction. The next is nucleus size. Size of a nucleus is expressed in terms of nucleus radius. The experiment conducted by Rutherford, scattering of alpha particle experiment and scattering by electron and neutron scattering revealed us the nucleus size. The nucleus size is the order of femtometer or fermium. That is, the nucleus size is approximately on the order of Fermi, that is approximately 10 raised to minus 15 meter or 10 raised to minus 13 centimeter. Various experiments based on the scattering of alpha particle, electron and neutron led us to the conclusion that the nucleus radius R, radius of a nucleus R, is given by the equation R is equal to a constant R0 into A raised to 1 by 3, where A is the atomic mass or mass number of the particular nucleus. So we can say that R, the nuclear radius, is a quantity that will not change proportional to, with respect to A, they are only proportional to cube root of A. That means, as the mass number or atomic mass changes, the radius is not changing proportionally, but it only changes only the cube root of A. So there is not much change in the nucleus size as the atomic mass or mass number changes. And R0, the constant R0 that obtained from the experimental measurement that I have mentioned, when scattering has been revealed us that the value of R0 is 1.4 to 1.5. Okay, it can vary 1.3 to 1.5. Don't bother about that, into 10 to the power of minus 15 meter. So that is why, as mentioned, the radius of the nucleus is the order of 10 raised to minus 15 meter, or it is the order of Fermi or femtometer. Okay, it is the order of Fermi or femtometer. That is 10 raised to minus 15 meter. You can simplify as Fermi. So the nucleus radius, the nucleus size is represented by the nucleus radius. The size of the nucleus is extremely small, of the order of 10 raised to minus 15 meter. That is of 1 Fermi, and that is given by the equation R is equal to R0 and A raised to 1 by 3, where the constant R0 obtained from the experimental measurement of the scattering alpha, beta or neutron revealed as 1.4 to 1.5 into 10 raised to minus 15 meter. Okay. So it is a quantity that is only proportional to the cube root of atomic mass. Then that is the nucleus size. The second is nuclear volume. Nuclear volume. The nuclear volume, assuming the nucleus to be spherical, that is the most assumed dimension, size, shape of the nucleus spherical. Assuming nucleus to be spherical, its volume V is equal to 4 by 3 pi r cube. So reducing that is 4 by 3 into pi into 1.5 into 10 raised to minus 15, the whole cube, A, the whole cube, A raised to 1 by 3, the whole cube goes, so that's equation. Now all this constant you put outside, 1.5 into whole cube into 4 by 3 into pi, that nearly comes to be about 14.09, 4 by 3 into 3.14 into 1.5, the whole cube, okay. You look at 4 by 3 into pi 3.14 into 1.5 the whole cube, that comes to be around 14 points, 14, plus 14 into 10 to the power of minus 45 into A is the mass number, or that is equal to 1.4 into 10 raised to minus 44 into E. What I wish to mention, stress you that the nuclear volume, the volume of a nucleus is an extremely small space. Okay, volume is a three-dimensional space. So volume of the nucleus is extremely small, of the order of 10 raised to minus 44, and it is meter cube. Okay, meter cube, and is proportional to the mass number A. Mass number B means it is proportional to the nucleon number. It is a number of proton. Mass number is the number of proton and number of neutron inside the nucleus. So it's a quantity that is proportional to the nucleon. Okay, that's very important. So volume of a nucleus in an extremely small space, so the quantity of the order 10 raised to minus 44 meter cube, and it's a quantity that is proportional to the nucleon number or mass number A. Okay, I mentioned the two property in connection with the size, dimension. The next is nuclear mass. Nuclear mass. As you know that the mass of an atom is entirely the mass of the nucleus. It is not the mass of the electron. Mass of the electron is negligibly small. It is 0.00005. Okay, not 555. Here is negligible. The mass of the atom arises from the mass of the nucleus itself. So the nuclear mass is the, you know that it is 1.66 into 10 raised to minus 27. Okay, 27 kilogram. Where ESUR is, remember? 1 atomic mass unit. Okay, is 1.66 into 10 raised to minus 27 kilogram. This is the mass into A. Suppose A is the mass number of any nucleus, then the nuclear mass in kilogram is mass of any nucleus in kilogram is, so mass of A is 1.66 into 10 raised minus 27 into A kilogram. Okay, that's the thing. Therefore, the density of the nucleus, rho or D of nucleus of mass number A, D is equal to, you know the density is mass per unit volume, mass divided by volume. This is the mass, nuclear mass M. Mass per unit volume. You put this value, that is equal to 1.66 into 10 raised to minus 27 into A, so much kilogram, divided by volume 1.4 into 10 raised to minus 44 by A meter cube. So what is the answer here? The numerical value comes to be nearly 1.66 divided by 1.4, the answer nearly 1 approximately 1 into 10 A get cancelled, 10 raised to minus, 10 raised to big one is 17 minus 10 raised to minus 27 minus 10 raised to minus 44, that is 17 kilogram per. Okay. Somebody, you look into the density of the nucleus. Now I drag your attention. Now I seek all your attention, drag all your attention to look into the magnitude of the density of the nucleus. It is a tremendously large quantity. You will get astonished on seeing the density of the nucleus. That the density of a nucleus is 1. It is a tremendously large quantity. The order of 10 is 17 kilogram per meter cube. 10 is 17 kilogram per meter cube. That is 10 raised to 9 gram per cc, or 10 raised to 8 ton per meter cube, something like that. Okay. You remember, this is an extremely large quantity. Okay. That means, what it means? What will be density? Density is the mass per unit volume. That is the accumulation of a mass within a volume. That it indicates that the density of the nucleus is a tremendously large quantity, of the order of 70 kilogram per meter cube, and is also independent of the mass number of the nucleus, mass of the nucleus. It is always a constant. The nuclear density of any nucleus is a constant quantity. When we start from hydrogen up to uranium, we can say that density of the nucleus is almost a constant, 10 raised to 70 kilogram per meter cube. It is independent of mass number A, or mass of the nucleus. or atom weight of the nucleus. And it is a tremendously large quantity. That I wish to say. 2 point. Nuclear density is independent of the mass of the nucleus, or mass number of the nucleus. And next, it is an extremely large quantity, tremendously large quantity, of the order of 10⁻17 kilogram per meter cube. That means 10⁻17 kilogram of mass is concentrated or accumulated within a volume of 1 meter cube. You consider a box or sphere or radius 1 meter cube. Okay, 1 meter cube, you consider radius a sphere or radius 1 meter cube, or you consider a rectangular box like the radius 1 meter cube, a cube, you consider a cube, of radius of breadth, length, height, okay, 1 meter, then the volume of the cube is 1 meter cube, or you consider 1 centimeter cube of material or cube, okay, anything like that. It is that within a 1 meter cube, 1 meter height, 1 meter breadth, 1 meter length, a cube, and within that cube, how much weight is concentrated? 10⁻17 kilogram. What happens when within a 1 meter cube box or cubic box, when you are trying to concentrate 10⁻17 kilogram of any material? That will definitely lead to explosion. That will lead to explosion that is not stable. That will definitely lead to explosion, and such a system will highly unstable. That's the mechanism of explosion. Okay, any explosive, then we try to expand anything suddenly within a small volume, or when we try to concentrate heavy mass into within a small volume, that will lead to explosion. That is the mechanism of any explosive. So you look, a nucleus is an entity in which a heavy mass of the order, tremendously heavy mass of 10⁻17 kilogram is accumulated within a small volume. Yet, what I want to stress is that nucleus is a stable entity. Nucleus is a stable entity. That I want to stress before the students, before you. In spite of the tremendous accumulation of heavy mass of the order of 10⁻17 kilogram within a volume of 1 meter cube, the nucleus is extraordinarily stable. You know that? Any attempt to break the nucleus, that is called a fission, it is very tedious, very difficult process that only happens in 1944, something like that. That year, after so many results. And no, it is not easy to divide the nucleus. Simply, it is not easy to fuse the nucleus. So anything that will destroy the nucleus is very difficult process. Okay, that means the nucleus is stable. Suppose you look around us, if our universe or our earth would not be stable, we cannot live here. Why we are living here? Because all our systems are stable, because the nucleus is stable. That's the thing. If you want to break the nucleus, we got to break it with the difficulty by atomic fission. Oh, it's a very research subject. Okay, it is happening. The fission is there, but it occurred only after a very tedious work. Only we can subject the nucleus to undergo fission. That means nucleus is very stable. That is why Earth is there. But we are here. Okay. So what I want to mention, draw your attention, is that we have to account for the extraordinary stability of the nucleus in spite of the accumulation of heavy mass within a small volume. That aspect will be discussed in this class. Thank you very much for listening to my class. I am going to wind up the class. Okay.